video again there. That'd be great. Have to upload a 6-hour lecture then to all right. So here we are again. We're kind of going to, well, I guess the last, what do you guys have, about 4 weeks left, basically, what it is? We've got about 2 weeks until Easter, and then 5, something like that maybe. So the last, let's say, 5-ish weeks there of class, I guess we kind of hit on these, what I would call special topics, right? There's been kind of a flow to things so far, and then we kind of started learning about how the molecules interact, and and then we talked about, okay, when they interact, can a reaction happen, and how fast that is. All right, those are kinetics, and kinetics flows naturally into equilibrium, right? And equilibrium, we talked about which side of the reaction is favored and the influences on that. And from there, we went into a specific topic discussing acids and bases, and then into buffers. That kind of, in my mind at least, kind of all flows together to tell a story with that. The next kind of couple of chapters here, just kind of we dip our toes into bits and pieces of what we've talked about in the previous chapters, and even going back to general chemistry. Today we're going to probably, I'm almost 100% certain, we'll come back to this idea of Q and enthalpy, right? Which is something we haven't really talked about all that much since the first semester of general chemistry there. But we're going to kind of answer the question of how do we know if a reactions even happen, or why do reactions even happen to begin with. And we'll talk about the idea of spontaneity in the universe and all these kind of things here and there. So when I say that we're kind of hitting on these special topics in my mind, I don't mean that they're not important or relevant or all these kind of things. What I mean is that they're, from the way that I see it, they're a little bit disconnected from what we've been talking about before, right? Especially when you get to the electrochemistry part there. That chapter always kind of makes me scratch my head why we put that in where we do, but whatever. That's what the American Chemical Society wants, so that's what we teach, right? Is what it is. But that's okay. So today, though, we're going to get into this, I think the book kind of calls it thermodynamics there, but we're going to be talking just about how can you look at the energy of a system, right? And so we're going to talk a little bit about different, well, first we're going to talk about distribution of energy, right? So where is the energy in a system, right? And where is the energy in the surroundings, and where is the energy in the universe, right? So these kind of ideas there, which, if you guys are remembering or recalling from the thermodynamics chapter in the first semester, we talked about the energy of the universe, and it has to remain constant and all these kind of things. So we're going to be bringing back those same kind of ideas here, except we're going to learn that in some cases the distribution of energy isn't constant, right? So we'll talk about that when we get there. So that's going to be kind of where we'll walk through in chapter 19 there. And then we'll use one of those ideas from chapter 19 a little bit when we talk about electrochemistry is what it is. And then from there we kind of talk about some organic chemistry and inorganic and all these other kind of little bits and pieces and odds and ends that we've kind of jumped over to get to the point that we are. So we got a little bit of work to do for the rest of this semester is what it is. All right. So, but before we get started, as usual, we'll open with some prayer here. Then we'll start looking at the new ideas. But Lord, we just thank you for another blessing, and we just thank you for another day. Lord, we just thank you for the opportunity that we have just to gather together again, Lord, and just to learn a little bit more about you and the things that you've created and the things that you put around us, Lord. We just pray that you just open our eyes and our ears, Lord, just to understand what it is that you would have us understand, Lord. Just help us to take this in and look at it in the perspective of the things that you've created, Lord, and how we can use this to spread your glory and the things that you would have us do with that knowledge, Lord. We just pray that you calm our hearts and calm our minds today, Lord, as we go through this day. And we just pray that the distractions in our life become focused, Lord. We pray that we can turn our eyes to you, Lord, and just focus on that, Lord, and learn how to lay our troubles before you. And just pray this in your name. Amen. All right. So, We'll talk a little bit here about thermodynamics, but a lot of what we're going to be doing for this chapter is I'm going to be giving you guys a lot of definitions and ideas and concepts, and then at the end we'll spend a couple days working through some problems and see how we can relate this all together. I kind of have to give you guys everything in a chunk in my mind, at least I have to give you guys everything in a chunk, and then we can go back at the end and take a look at the specifics of how these things all tie together is what it is. All right. So, one of the important things that's going to come up over and over and over, excuse me, in this chapter, and one of the things and the common questions and that kind of stuff is the idea of a spontaneous process. Okay, so we'll ask, is this process spontaneous? Is this reaction spontaneous? Okay, these kind of things. And so, what does that mean? Well, they proceed with any outside assistance. Okay, I think you guys got that, right? You know, that's not too complex yet. Processes that are spontaneous in one direction are non-spontaneous in the reverse. Okay, so that's this idea of equilibrium. They're kind of just poking its head out there, right? Can we proceed in one direction or not in the other? Okay. And I think this is the actual photo that you guys have in your book there, which is I find hilarious, right? They bought some eggs, they paid somebody to be a hand model and dropped eggs onto a counter, right? So, science. All right. But anyway, right? Don't confuse spontaneous with fast, all right? So that's not what we mean at all. That's two separate ideas. There's spontaneity and kinetics are separate concepts, right? That's why they're in separate chapters. We didn't talk about spontaneity when we were going through the kinetics chapter there, okay? There are fast and slow reactions that are spontaneous. So if there's a question that's asked about, is this a fast spontaneous reaction, then we have to bring in this idea of kinetics into that also, okay? And don't confuse non-spontaneous with impossible, right? Energy we can use to create some reaction spontaneous that would otherwise not be. Okay, so that's one of these ideas that's going to come out of this also here, right? We can overcome certain aspects of spontaneity if we add energy into a system, okay? Now you guys already knew that, right?
Yeah.
The natural progression of things is to disorder, okay? And there's interesting philosophical arguments that come from that also, right?
That's not there with philosophy.
Well, I mean, science and philosophy are inherently linked, right? So, but let me ask you guys a question. So you guys moved in at the start of this semester, right? And your room was cleaned, I hope, and before you guys moved in, yes? How's the status of your room now?
Not that bad, because there's room checks tonight.
Mm-hmm. So to get ready for those room checks, did you guys have to go around and clean everything and hide everything and put everything in the box that the RA can't see through?
If you're insinuating there's vodka in my file cabinet, I have no idea.
I'm not saying anything. I'm just making a broad, generic statement that I can easily deny. Okay? But you guys, right? So you guys had to put energy into your room, right, to get it back into a state of order. You guys get what I mean with it? That's not a spontaneous thing that happened, right? We all wish that we would just go back home and ooh, it's clean, right? Finally, my roommate did something. No, right? Okay, right? We have to put energy into something to overcome the spontaneity, right? Your room gets dustier just by virtue of existing, so to speak, right? You have to go through and wipe everything down to overcome that disorder that happens. That's all we're talking about here, okay? Just because it's non-spontaneous doesn't mean impossible. We can add energy into the system to overcome that, okay? All right, so some more questions that come out of this, or things to think about as we're going through, or why are equilibria product or reactive favored, right? So again, a little bit of our ideas there from the last 3 chapters coming back. Why do some reactions occur spontaneously? Why do others need that energy input for them to happen, right? Exothermic reactions are often product favored, but not always, and why might that be, right? And so these are some of the things that we'll be going through and thinking about and asking as we kind of walk through this chapter is what it is, right? So why or how can we start to answer these given the tools that we have available to us for this semester, for this course is what it is.
Hold on. That mess is basically just dropping aluminum foil into bromine.
Mm-hmm, yep.
Oh, that's very cool.
There's some cool stuff.
Would the same thing happen with iodine by any chance?
Yep.
So if we took like a bottle of iodine from the first aid section of Walmart and dumped aluminum foil on top of it?
No, that wouldn't do anything. That's a solution of iodine, right? So it'd be, you'd have to isolate the iodine from there by itself, is what it is.
Any tips on how that might be accomplished?
That I certainly will not answer. There are far too many nefarious things with elemental iodine. Anyway, so one of the ideas or concepts that come out of this chapter is that energy will spread out unless it's hindered from doing so. Okay. Well, it's not that we can like put energy into a bottle and keep it from going somewhere, right? You know, that's not quite what that means there. But the idea is that the natural tendency for energy is to want to spread out. That's really what that statement is saying, okay? If energy can disperse out, it will. You guys kind of already knew that, right? That's why we have thermoses that are insulated. Otherwise, you know, if that statement wasn't true, then your coffee would remain perpetually hot, right? The heat wouldn't want to go anywhere. But as we know, coffee, you know, cools down, right? Because the heat or the energy that's in the water molecules, right, gets transferred to the surroundings. The energy gets spread out, okay? So again, there's that statement about exothermic energy is transferred to the surroundings, right? The bond energy, right, the potential energy is dispersed into many more atoms and molecules. That's where the energy is coming from there, okay? Remember, exothermic means that we release energy as we're going through and reforming our bonds. If you think back to how we approached one of the calculations for energy in the first semester is that we broke every bond apart and then we reformed every bond. It takes energy to break bonds and you release energy when you make bonds, okay? So if you make new bonds and there's an excess of energy, it gets spread out, okay? Which is something the universe enjoys. So dispersal of energy is probability driven. We'll talk about this a little bit here, right? Energy is more likely to spread out over many atoms over just a few, okay? So we'll talk a little bit about how we can measure that, sort of, right? We'll kind of do a little bit of hand waving and assumptions and these kind of things. But we can get a measurement for the probability to disperse energy, okay? Good. So if we take this idea and kind of visualize it, there's a couple other examples in the book that I'll show here in just a second too, right? So what's the possible outcome if two excited atoms make contact with two more atoms? So if you want to think about what does it mean in this context where we're talking about excited atoms, they just have excess energy in them, if you want to think about it like that, right? So they're really, really happy for some reason, right? And so if they contact two more atoms, what's going to happen to it? Well, the idea is that there's going to be a transfer of energy between the different atoms that are involved with this. And so if we list out all the different possibilities of what can happen, right? A and B can retain the energy, or B can transfer it to D, or A can transfer to D, or both can get transferred to D, right? That's all this is showing here, okay? You guys with me on that? We're just spreading out the energy over different systems. So within a relatively small number of cases, right, the energy only stays in some form, right, with one of the original atoms in 30% of the time, okay? So there's a 70% chance that the energy will disperse, right? The more atoms, right, energy concentration is much less likely, aka the more different, right, the more components you add into the system, the more likely it is that the energy will spread out, is what it is, okay? So we contained ourselves to a relatively small sampling of just 4 total atoms, and we've already got 10 cases with it. So you can see how this exponentially starts to get worse as we, well, not worse, so that's not what I mean to say. The probability exponentially decreases as we go through and add more things to our system, is what it is, okay? So now if we take that idea and kind of visualize it to something that you guys are already familiar with, right? Energy is dispersed when a system expands, okay? Gases expand to fill a container. You guys know this. This is one of the first definitions that we had way back in the first semester of Gen Chem in Chapter 1. When we talk about kinetic molecular theory and what are some of the ideas that come along with the different states of matter, the solids, the liquids, and the gases, right? So on the quantum level, energy levels for gas motion, right, get closer together when volume expands, okay? Now, what does that mean for us? Let me try and translate that fairly complex statement a little bit differently, okay? The closer the energy levels are for a system, the more easier it is to hop in between them, is what it is, okay? That's all it's talking about. So the closer in energy, right, the easier it is to kind of hop in between those, the more accessible they become. So if you watch some of these videos or read different textbooks or different chapters and all this kind of stuff, they talk about accessible energy systems, okay? Right, energy has to hop around between molecules and atoms, and the easier it is for them to do that hopping, then the more it's going to happen. That's all it's really saying there. So more energy levels become accessible at a given temperature when things expand, right? And energy will disperse over more levels. So these are all the consequences of what's happening in this case, okay? So if we have two separated containers there, and then we have a gas that expands in between them, right? This is the reason why that happens. All right. I always like this photo. Can you imagine if that's like, you know, if you do something famous in life and that's a statue that gets put up of you, you just look angry and displeased at everybody who comes by. Angriest looking statue. Anyway, I don't know, I find it hilarious. But so what's going on with this here? So processes are product favored if energy is dispersed from a few levels into many levels. Wow, that's something you can put on a magnet and put it on the back of your car or something, okay? So we'll talk about it and we'll give a definition of this in just a second here, okay? But that's the idea to kind of to think about. This typically occurs for exothermic reactions, we talked about that, and processes in which matter is dispersed, aka you can spread things out more, okay? So these ideas here, I'm just kind of summarizing what we were talking about in the previous slides here is what it is, right? So if you have to describe an answer on an exam or something like that, I'm looking for these kind of phrases when you guys do discuss that system, right? So here we go, right? In thermodynamics, nanoscale energy dispersal is measured by the entropy of a system. Okay, there we finally get to it. So entropy is one of these terms that I think we've heard colloquially used in many different situations, and it always tends to mean something a little bit different, I guess, within the context. But so within the context of general chemistry, we're talking about the energy dispersal for our system. So entropy is just basically a way of us measuring where the energy in a system is. Not necessarily how much. That's more enthalpy, right? Enthalpy tells us how much, entropy just tells us, you know, how dispersed it is, if you want to think about it that way. Right now, the grumpy looking guy up there is Boltzmann, and if we were going on into a more advanced chemistry, do you guys talk about Boltzmann distributions in biochem? Okay, I didn't know if that was something that came up in there or not. But so the equation that's sitting above his head there, S equals K log W, that's the Boltzmann distribution or the Boltzmann equation. If you take a look at Wikipedia, it'll tell you about what the different stuff means. But it's just a way for us to calculate the entropy of a system. That K that's up there is nice because it's not a K that we've dealt with before. Although, right, we've talked about K for rates, and we've talked about K for equilibrium, and there's other, right? So that is the Boltzmann constant. So really it's KB. And then log of W, W is not work. It actually represents the German word for probability, the Wahrscheinlichkeit is what it is. So just how often does something happen, okay? So entropy is just some kind of constant multiplied by the log of the probability is what it is. And it's really useful for us to calculate certain properties of a molecule or a system is what it is. So very, 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 very important if you guys ever have to take P-Chem or physical chemistry, which don't, right? But I'm just kidding, right? If you guys have to take physical chemistry, that'll be one of these very, very important ideas that come up. Yeah, what's up?
Just curious, is that K, is it K capital V?
Yeah, lower K, well, K sub capital V, yeah.
Okay.
Yeah.
It was in your sheet for exams, the formulation.
Oh, yeah, yeah.
Are we gonna have to use it?
You never know what the world might hold in store for you. Alright. So how do we measure the dispersal of energy, right? So at a constant temperature, right? The final entropy minus the initial entropy is going to be our change in entropy. And that for us is going to be equal to lowercase q over t. Okay, so what is q? Well, remember q is just the way that we measured the energy of a system, right? Our enthalpy. And we said that under constant pressure, right, q is equal to delta H. Right? Essentially, q and enthalpy are the same as long as there's no work being done. If you look way back in your notes, you'll see that, we talk about enthalpy is equal to Q plus W, although if there's no change in pressure or volume and that kind of stuff, then we can just kind of leave that work factor off of it, is what it is.
I thought Q was MCAT.
Mm-hmm. That's it, yeah, it is.
Okay.
Yeah. I'm just saying those are essentially the same under specific conditions. Yeah, the way we can calculate Q is M times C, right, times delta T, yes. Yeah. Okay. A reversible process, right, just to kind of put some fine points on this, can be reversed with a slight change in conditions, right? Melting ice and changing the temperature will cause it to refreeze again, right? The dropping of the eggs is not reversible, so to speak, right? So under the right conditions, we can apply this. I believe, yeah, okay. So let's see just a quick typical example here of a question. So calculate the change in entropy when 25 grams of aluminum melts, right? And then it gives us some numbers and stuff. As I mentioned there, this is a reversible process. We're talking about melting something in this case, right? So it can be refrozen if we change the temperature. I specified you got. Oh yeah, right. If you're ever dividing by a temperature, it has to be in Kelvin. Right, so that's the point here, right? So if you'll notice, I gave you guys some information. I tell you a specific temperature, which you'll need, and then I'll tell you, and I'll specify that it's at 1 atmosphere. Now, is the 1 atmosphere all that important? Not really, the point being this is at a constant pressure, though. At a constant pressure, right, Q is equal to delta H. Pay attention. What units are delta H in? Not just kilojoules, per mole. Right? When we're talking about entropy, we're usually in units of joules per Kelvin, is what it is. Right? Some measure of energy per temperature. You guys following along with this? You guys catch what I'm saying? Do we have a mole of aluminum that's melting? No. How much do we have? A couple of grams of it. Got it? H, 10.7 kilojoules per mole divided by our absolute temperature. Divided by 5. So we do all that, I got what, 0.0106 kilojoules per Kelvin. Okay. And then if the question asks in joules or some other value here, just don't forget to go back and change that, but this is just fine. So important things to remember here, okay? Remember, if you're dividing by a temperature, that means that that temperature can never be equal to 0. That's the only scale that temperature can never equal 0.
Celsius?
Kelvin, right? That's one of the whole points of Kelvin, right? Practically speaking, we'll never get temperature equals 0 Kelvin. We're given units of delta H, right? We're given units of delta H in kilojoules per mole. So we need to pay attention to how much we're melting or freezing or whatever it might be. Got it? If we have 25 grams, we need to make sure that we have the correct units for stuff with that, right? Units for entropy are usually going to be some form of energy per Kelvin is what it is. Joules per Kelvin, kilojoules per Kelvin, something like that. Good? Not too bad, right? All right, so let's talk about a couple more things here to think about, right? Some things to kind of keep in the conceptual back pocket. So the entropy of the universe increases in any spontaneous process. Okay, so what this means, and one of these things to kind of think about, is that entropy is always going to have a positive value, right, when we're going through in a spontaneous process. Okay? In a couple of slides or towards the end of this chapter, we're going to start to say, hey, is this process going to be spontaneous or not? And we're going to have to compare entropy and enthalpy values and make an assessment based off of their relative magnitudes. Right? Are they plus or minus, and how much of a plus or minus are they? Okay? So if we think about what this means mathematically, a reversible process means that the system and the surroundings equals 0. Okay? There's no change in entropy. An irreversible process means that this has to be bigger than 0, because the entropy of the universe has to increase. Okay, that's the nature of what's going on. Okay, everything's tending towards this order is what it is. So if you think about this, what does this mean? So if delta S has to be bigger than 0, that means that, right, one of these has to be smaller than the other, right, or one of them has to be bigger than the other. You guys with me on this one? Right? So one of those two values in the equation there has to be slightly bigger than the other one is for that to hold true. So we have to be careful because it's a little bit different. Remember when we were dealing with Q's, the enthalpy, and we had those types of problems of, okay, you take a hot piece of metal and you put it into water. Right, we said that the Q of one is equal to the negative Q of the other because energy had to be maintained. Okay, but that's not the case for an irreversible process. Right, we can't set up that kind of equation there, right? Because that's only true for a reversible process where we can make that kind of statement. So we have to be careful just about the way the question's asked or the information that's given with it there. Remember, the universe wants you to break eggs. That's all this is saying, okay? So a perfect crystal at absolute 0 has minimum molecular motion, right? Minimal energy dispersal, yada, yada, yada. S equals 0. Okay, so that's kind of basically what the third law of thermodynamics says. Okay, so under specific conditions, right? Everything stops moving at absolute 0 might be the colloquial way that we say that there. Okay? So if we can measure the heat change from 0 Kelvin to room temperature, right, it gives us delta S and the absolute S and T at room temperature there, okay? So we're just saying, how can we start to measure this, or where do the numbers come from? Okay, because if you take a look in the back of your book, I forget which exact appendix it is, but it's got a giant list of these different S values for you guys there, which are useful for different equations to calculate different ideas from. So how do we get that, right? So this is all we're talking about here, right? So that's the equation that we used, and we can figure out the entropy at room temperature there just by doing a little bit of rearranging this depending on what the temperatures are, okay? All right, so a couple of things here. So if you see an S with a little degree symbol there, that's S naught, right? All we're talking about there is the standard molar entropies, right? They heat 1 mole of a substance from 0 K, usually at 25 degrees Celsius, okay? At a constant pressure. Now S naught has units of joules per Kelvin per mole, right? That just makes sense given how they measure these things, right? They heat 1 mole over a range of temperatures, and we look at the energy with that, okay? Now the statement in the book, and the statement here on the slide says, hang on a second, right? The statement in the book and the statement on the slide says that S naught is always positive for all materials. Does that make sense? What does that mean? It means we're increasing entropy. Does that make sense? If we're starting at absolute 0 and we go with the assumption that there's no motion, what happens is we start to raise the temperature. We're adding what into the system? Energy, right? And that energy causes what to happen? Molecules start to move around, right? They start to vibrate, they start to shake, they start to bend, they start to twist, right? All the different molecular motions that are associated with increasing energy in a system, okay? And as that example, if you remember previously, with the 2 gases there, right? If we start to take up more space, energy becomes more accessible, different energy levels become more accessible, so we start to increase the entropy of the system, is what it is. Things tend towards disorder, that's all. What's up?
Okay, so stupid question here.
Mm-hmm.
But if stuff never actually, in practical experimentation, it's impossible to actually get something to absolute 0. How is this, useful or applicable?
How is what useful or applicable?
This thing, assuming that you're dealing with something.
How cold can we get something?
Is it really possible to get something to reach absolute 0?
No, I didn't say that though. How cold can we get something? Really, really darn cold is the answer, okay? We can get pretty darn close to absolute 0. Now I'm not saying there's I genuinely don't know, but I don't think there's a group of scientists out there that are, okay, we need a mole of aluminum, and they back up the truck and then they stick it in a giant freezer and they start to measure it, right? But that's not what we need to do either. So if you think about it, right, the way that we do science to predict some things, right, is if we gather enough data, we can draw a trend from it, right? So we can get things practically cold enough pretty darn easily, right? Liquid nitrogen is pretty accessible, right? Even liquid helium is fairly accessible. So we can get things to cold temperatures and kind of extrapolate from there also, right? So to be honest, it's a good question, right? Exactly, how cold do they get things to be able to predict S naught values, right? Maybe they do, I don't know. So they get it pretty cold, and then they do use a little bit of math to get the rest of it, right? I'm sure that's what it is. All right, so there's tables of this everywhere, right? I just put something here just to give you guys kind of a view on what things are and how the book kind of lists these things out. So if there's a table, always something good to do is take a look at it and say, well, first of all, the most important thing is always, what are the units for the things that are presented in here, right? So these are molar, standard molar entropies, right? And so joules per Kelvin per mole. We have carbon as graphite, carbon as a gas, methane as a gas, ethane, propane, all these different things here, right? So state is important, okay? So water, let's see, is Don here? Yeah, it is, right? So water as a gas and as a liquid have different values here. So when you guys are going through and you're using these values to calculate something from a reaction, you have to pay attention to the state of the matter, okay? Very important again. In the past few chapters, we've been dealing with things that are all in solution. So we just kind of make an assumption that, okay, everything's aqueous and we add things together, okay? Here we have to pay close attention again to the states that things are in. So let's talk a little bit about some qualitative guidelines for entropy, right? AKA let's explain why this is important or how we can use these kind of things type questions, right? So the entropy for a gas is much greater than that for a liquid, is much greater than that for a solid, right? That's what the statement at the top there is saying, right? Gases have a much, much higher entropy than liquids, and liquids have a higher entropy than than solids. I can tell that you guys are all shocked because you guys have to take a seat and just, to steady yourself from that statement there, right? Does that make sense? Is your desk in front of you here, suddenly accessing more energy levels? Like I sure hope not, right?
What if it was a desk with an electric plug-in?
Sure. Right? But the point is this, right? So again, if we're thinking back to this, the visualization there with the two gases in the separate bottles, right? Your desk isn't suddenly trying to spread itself out over this entire room, right? It's locked in that state right there, okay? It's not going to change shapes. It's not going to change size. It's not going to change mass. It'll increase and decrease temperature a bit, especially in this room where it's always friggin' cold, right? Right? But you guys get the point with this? There's not much change in the entropy going on there. The molecules are moving around about the same as they always will be, right? But if you imagine the liquids in your thermoses or a gas in this room, right? The gases are zipping around over this entire room, okay? Many different or many closely related accessible energy levels, all right? So when you're doing a reaction and the question asks about to make some kind of qualitative statement about, hey, does entropy increase or decrease for this system? One of the most important things to pay attention to is the state that things are in, right? If you start as a solid and you go to a gas, right, you're dramatically increasing the entropy of that system. Okay? Does that make sense? That's all I'm telling you guys to pay attention to with this, right? The different states of matter increase or have more or less entropy associated with it. Yeah, okay, so that's how I think it's all. I don't need to talk to you guys about that stuff. You guys have eyeballs, you guys can see it. Okay, so larger, more complex molecules have higher entropy. All right, so we talk about this a lot when we get into organic chemistry. Okay, so if you have the more things you can string together, right, the more things or atoms that you have together in one molecule, they're going to have many different accessible orientations. Okay, so real brief, and we'll talk about this a little bit more at the end of this semester when we talk about organic, right, we give our introduction to organic chemistry. But when we draw a Lewis structure for something like C3H8, right, we just have a bunch of atoms that are connected by lines, and that's what we put on paper. Okay? But in reality, that's not the case. Okay? Bonds can twist, bonds can rotate, the whole molecule can flip. Right? Each atom can rotate or spin or bend or stretch or play the accordion. They're just bending back and forth in all different manners. And so the more atoms that you have, the more bonds there are for these things to happen with. Okay? Now we can actually measure that really easily. We can see indirectly, right, the bending and the stretching of different atoms in a molecule. That you guys aren't impressed with that, you're not listening to what I'm saying, right? We can actually see the different bending and stretching of the bonds within a molecule. It's faster. You guys can go do it. I can show you guys in 30 seconds upstairs, okay?
What?
We've got a fantastic instrument that we have to measure that kind of stuff with. That's infrared spectroscopy. Tells us about these kind of things, okay? We can see the different molecules and bonds within a molecule, kind of bending, stretching, and flexing, and doing all those different things there.
Seriously?
Mm-hmm.
How does that work?
Good question. Take my organic chemistry class and find out, right? With a low price of, how much do they charge you guys now? Again, I'll tell you what, if you guys all sign up together, we'll give you a bulk discount. How's that sound? But anyway, right, so we do talk about that, and it's very important because we can actually fingerprint molecules. Right, so if any of you guys are interested in those, what are those, like those those shows where they like solve the murder and they like put it into different instruments and they get you the data out of it, right? That kind of stuff that's always very hyped and, you know, sterilized for television there, right? But infrared spectroscopy is one of these first things that they really do when you have an unknown, right? It's a non-destructive method for figuring out what in the world you guys have here. Because we can see the different bending and stretching and we can relate that back to what molecules and functional groups and atoms are present within a molecule, right? So a very, very, very important technique comes out of this. But anyway, so what do you guys need to think about this? The bigger the molecule, the more things can stretch and bend and move within the molecule itself, right? That's the idea here, right? It can kind of bend and stretch within itself, okay? So that's the statement down here at the bottom, okay? So if we move to ionic solvents, like covalent solvents are, we'll talk about them, but ionic solids, right? So the weaker the ionic forces, the larger the entropy. Okay, so again, I make statements like this. Your first thought should be, really? Right? Are you sure? Does it make sense? Remember, you might not believe me now, right? But chemistry is a science. Like, okay, I do believe that, okay? And if it's a science, it has to be logical. You're like, okay, now I'm skeptical, right? But the point being, there has to be an explanation for us to make statements like this, right? So, a weaker ionic force means a larger entropy. Okay, well, first of all, what in the world do we mean by ionic force? Literally, we just mean the charges that are present, right? The Coulombic forces. What's up? Oh, that's right. I thought you were raising your hand up. Okay, so does it make sense then that we have a lower entropy for something with a +2 and a +2 and -2 charge than a +1 and -1? Well, remember what we're talking about is the motion of the molecules, essentially. So what happens here? So imagine you've got a sodium and a fluoride, right? So we got sodium and fluoride here. They're each +1 and -1. As we add energy into the system, these things are going to start to move around a little bit, right? What keeps molecules together? What keeps the universe together?
Bonds.
Yeah, right? And bonds are made out of electrons, right? So everything in this entire universe comes down to something negative being attracted to something positive. Got it? Everything. So if you're ever on an exam, you're stuck on a question, just say negative gets attracted to positive. Oh, what the hell are you talking about? This is a buffer reaction. But even there, right, the statement holds true, right? So, right? But this is the point, right? This is the point, okay? So if you think about this, if I have a bigger negative and a positive, what does that say about the attraction between those two?
Stronger.
It's stronger. So if we add more energy into this, these things want to start to play the accordion and stretch away from each other. You guys with me? But if we have a stronger positive or negative charge, what does that mean? It takes more energy, right? It's harder for them to play the accordion, is what it is. Got it? So they're not going to move away from each other as easily. Now we talked about this too, right? When we talked about the properties of ionic solids. Right? Things like in the last chapter, we talked about dissolving something. Why are some things soluble and some things aren't? Right? What happens to the melting point of solids as we change ionic solids as we change the charges? Right? All these kind of ideas are tied together here to come up with our coherent logical statements. Okay? Here we have something else that's going on too, right? We'll talk about the relatives. Well, actually, I don't think we'll talk about it here, but the relative size of the atoms compared to each other here makes a difference too. Okay, this has to deal a little bit with orbitals and that kind of stuff. So we'll bring that idea back in organic chemistry there. Okay? All right. So still along the same things here. Okay. If we dissolve a solid or a liquid, okay, so we start to make a solution of something. What happens then? Okay? Larger matter dispersal, okay, so we take a solid and we take some sugar and we dissolve it into water, okay? If we stir it around, we know that the entire glass of water that we have is going to have the same sweetness to it, right? There is no localized sweetness if we have a evenly dispersed glass of sugar water that we made, right? That entire system, right, is dispersed over a larger space, over a larger volume, right? And you'll notice I have an asterisk there, right? S usually increases, which means sometimes it doesn't, right? Strong solvation may increase order. Now, what in the world does this mean? So again, if we look back onto our chapter in, I think it was like chapter 4, where we talked about aqueous reactions. And that was where we first introduced the idea of what happens when you put an ionic compound into water, okay?
The water molecules attached to it.
Well, they associate with it, right? We talked about spheres of solvation. When you put an ionic compound into water, right, the oxygen of the water gets attracted, right, to the cation. And the hydrogen of the water gets attracted to the anion. And what they will do is they will order themselves in a manner around the different ions, okay? So there actually is a slight decrease in terms of the entropy of the water, okay? But there is an increase in the entropy of the solid that you're dissolving, okay? And it just depends on the balance of those two. By far more often, there's you are increasing entropy by dissolving something. You have to order a lot of water molecules. You have to order a lot of water molecules to kind of overcome the entropy of solvation there, right? But it is important. It actually is one of these ideas that we had in one of my first projects in graduate school was looking at nuclear waste extraction. We had to play with this idea of entropies of solvation to actually get the individual ions out of solution, right? So it actually is a very important scientifically to kind of keep this in mind here, that sometimes this is the case, okay?
So did you guys find a way to safely dispose of nuclear waste?
Yeah, we did, but it was too expensive, right? So no one's gonna do it.
Hold on, what was it though, for purposes of,
I'll talk to you about it later. I'll show you. Dissolving a gas. Okay. So gas molecule motion becomes restricted. So now you're making your soda, right? You've got to cram a bunch of CO2, which wants to zip around, right? And fill all the space provided to it. You got to cram it down into a contained solution, right? Into water. Now that doesn't want to really happen, right? Because if you think about it, a couple slides ago we said that, gases have higher entropy than liquids than solids, right? So if you think about when you're making a solution, I know I'm not, this isn't technically correct, right? You're essentially taking a gas and you're putting it into a liquid form, right? You're dissolving it. You guys with me on that? So remember, liquids have restricted motion when compared to a gas, right? So dissolving a gas into a liquid is not entropically favored, right? Delta S is less than 0 here, right? So there has to be a reason then as to why we can dissolve gases into water to begin with, and we'll talk about that. And we'll be able to answer the age-old question as to why do fish prefer colder water, right? Or some fish, I guess I should say. Right? This will be part of our answer for that too here, okay? We're gonna have to think of some other ideas to kind of, it's not just entropy that rules the world, right? Or rules the universe, so to speak, okay? We'll talk about this. So, thinking about, the state of matter, what interactions are present and how much it can move around.
is the cold water basically has more oxygen in it?
It does, but why? Right?
Because if it's a lower temperature, then the gas isn't trying to rise and escape as much?
Maybe, but why? There's a little part that we're missing, but we'll bring it back in, right? So a typical question here is, predict the entropy changes for the following reactions or systems or whatever the specific question is, right? So up at the top there, right, if we have calcium carbonate, it goes to form calcium oxide. and CO2.
Hey, this looks
And
familiar.
it does look familiar, doesn't it? So if we have a solid that goes to make another solid, there's not much of a change there, okay? So we couldn't really say too much about the entropy if we have one solid converting into another, right? But since we do form a gas, we expect there to be a large, right, increase in entropy because we're having this stuff zip around, right? We're having more accessible energy levels. The other point to think about is that how much of our stuff gets made. We start with one mole or one thing, and we end up forming two things with that. So we have two components that add into this idea of what the entropy of the system is. Okay? And for the second part there, they're all gases. S is approximately constant, right? We have 2 moles at the beginning, 2 moles at the end. The gases are constant, but there is a slight increase in entropy there. And that just has to deal with the nature of the bonds and that kind of stuff that's formed too, okay? So we can approximate things with this, right? And that's fine and that's fair, right? But in reality, sometimes we have a little bit of a deviation from what we might expect, okay? So a typical question might be, here's a reaction. What do you think is going to happen with the entropy, right? CO plus O2 goes to make CO2. Right? 3 gas molecules on one side, 2 on the other. I don't need to read this necessarily all out to you guys here, but the point being, does this stuff make sense to you? Could you guys give me an explanation like this back to me if I ask you about this stuff, right? Yeah.
Okay, I don't have a periodic table with me, so gonna be a very stupid question. But would an ionic thingamabob made of like, Andy, can I borrow your periodic table for a hot second? Okay, if you had an ionic compound made of like barium and iodine, would that potentially have like enough of a charge and stuff happening that would be able to overcome the entropy thing of water to the point where the overall reaction has a decrease in entropy?
No. Probably not for that. It's not necessarily just how big it's more related to this, the charge. The magnitude of the charges rather than the size of the atoms.
Would the maximum charge be 3 though?
For what?
For ionic?
No. We can get other charges than that.
Is there a maximum ionic charge?
Yes, but it's dependent on the atom, right? Because it depends on how many valence electrons there are.
So what's like the atom that can have the strongest ionic charge?
Good question. I'm not sure, to be honest. I'd have to go look it up.
What, do you at least kind of know what the trend would be?
The trend
For like size of ionic charge potential?
Well, yeah, I mean, you're going to look for something in the transition metal block there.
Okay.
Right, something in your D block, probably in your 3D metals there is probably going to be your highest charge,
Okay.
right? So something like vanadium typically gets to a +5 charge. Whether that's going to be soluble in water or not is a different question, right?
Interesting.
Okay, so hopefully you guys got that. All right, so we'll end with this thought here, and we'll pick up a couple of questions next time. So now we've talked about the qualitative side of things. I can give you a reaction. You guys can answer the question of, hey, does entropy increase or decrease?
It's the evil E.
So if we put some numbers with this, right now we can start to calculate the exact value for it also. So entropy is a state function, right? Remember that just kind of defines the math that we can do with it, right? I think that's a simpler way of saying it, but how do we deal with this? So the delta S, right, of a reaction is equal to the entropy, the sum of the entropies of the product minus the sum of the entropies of the reactants there, right? So we have the equation. It needs to be balanced, right? And then we look in the back of the book and we find our entropy values for those units, for those molecules at the correct states, okay? And then we'll sum those up based off of how many of those are in our reaction. Sound good? So I think that's a good stopping point for today. We'll pick this up next time, and we'll continue talking about disorder.
Thank you, Doc.
For academic advisor this week.
Okay.